Dear students, in the last class we have studied about the three magnetic vectors B, H and M, and now we are starting the relation connecting the three magnetic vectors B, H and M. And B is the magnetic induction vector and H is the magnetic field intensity vector and M is the magnetization vector. When a piece of magnetic material is placed in a magnetic field, it gets magnetized. And the magnetism so developed in the specimen is called the induced magnetism. And this phenomenon of inducing magnetism in a specimen is called magnetic induction, and it is represented by the B vector. And the field that induces magnetism is called the magnetizing field, H. And due to magnetization, magnetic dipoles will be produced in it, and this magnetic dipole moment induced per unit volume is called the magnetization vector M. And this M, B, H can be related by a relation. And here we are deriving the relation connecting B, M and H. For that, consider a Rowland ring. A Rowland ring is a toroidal coil, and we are familiar with a solenoid. A solenoid is simply it's a coil of insulated copper wire wound over a rod-shaped form made of solid iron. And in the figure, you can see a solenoid coil. Here, the magnetic lines of force are straight lines in the case of solenoid. And when this solenoid is bent into the form of a circle, that will forms a toroid. That is, when a solenoid is bent into the form of a circle, that forms a toroid. And hence, in the case of a toroid, the straight magnetic lines in solenoid becomes the circular. And here we are considering a toroidal coil. And in the toroidal coil, we can remove and replace the central core. Let R be the radius and N be the number of turns of the toroidal coil. And when a current I pass through the coil, and it produces a magnetic field. And first we are considering a toroid without iron core. That is a toroid in which there is no iron core is present. And when a current passes through this toroid coil, it produces a magnetization or magnetic field, and the current I is called the free current which magnetizes the ring. And this current and the magnetic field can be related by a relation, and it is called the Ampere's law. The Ampere's law relates the current and the magnetic field. And here we consider in the second figure toroidal coil a blue colored loop, and this loop is called an Amperian loop. And generally an Amperian loop is a line which is drawn around a conductor to determine the magnetic field. And here consider the blue circular loop in the toroidal coil, and at any point on the circumference of this loop we can represent the magnetic induction vector B as the tangent. So at any point on the circle or the loop we can represent the magnetic induction vector as a tangent at any point. And also we can represent the whole circumferential length. We can divide the whole circumferential length into small dl elements. So the B and dl will be parallel. And here, according to the Ampere's law, the closed line integral B dot dl is equal to the current flowing through the coil, that is mu 0 times the current flowing through the coil, that is mu 0 Ni, where B is the magnetic induction vector. At all points the B is tangential to the path, and B and dl are parallel. Dl is a small element, and this dl combine together to form the whole circumferential length L. And hence the B is a constant. We can integral B dot dl, we can take B outside, and integral dl, it will give the circumferential length L, or if R is the radius of this circle, then it becomes 2 pi R. And hence in the case of a toroidal windings without an iron core, we can apply the Ampere's law. And here the current I is the free current which magnetizes the ring. And next we are introducing the core into the windings. And here the number of windings and the length, circumferential length of the windings, and the current is kept at constant. And because of the core, when the core is introduced into these windings, and because of this current flows through the material, and it produces a magnetic field, and it gets magnetized, the core material get magnetized. Then the magnetization, because of this magnetization, we have studied that because of magnetization, magnetic dipoles will be induced in it. Magnetic dipole means two unlike poles separated by a distance. That is, two opposite poles. One is a north pole and another one is a south pole separated by a distance, and it forms a magnetic dipole. Or a current carrying a loop behaves as a magnetic dipole. That is, when a current flows through a loop, and if the current is clockwise direction, then it acts as a south pole, and if the current is in the anti-clockwise direction, then it has a north polarity. So depending on the nature of the current flowing in a current loop, we can consider a magnetic dipole. So in the case of a toroid, here in the figure we are giving three pictures. One is a toroid with a magnetic core induced in it, and the second one is a toroid with an air core, and the third one is a slice section of the, we are slicing this toroid, then we are taking a section of this toroidal structure, and that represents in the third picture. And the first case, we are introducing a core into the windings, and because of this magnetic field, the core material gets magnetized, and the magnetic dipoles will be induced in it, or it can be represented as a current loops, and these current loop can be represented by small circles. And in the third picture, where there is a small section of this toroid is given, we can see small circles with a dot and a cross. And the dot means the current which is flowing into this, and the cross means the current which is flows out of this material. That is, in a toroid, when a current passes through the coil, it goes into the toroid, then it comes out at the same time. That is, it goes like as in the figure. First figure, we are representing the magnetic core. We can see the direction of current, that is, it is just as in the case of a coil which is wound over the core, the current flows into the coil, into the toroid, and it flows out of this toroid. And the current which flows into the material can be represented as a dot, circle with a dot, and the current which flows out can be represented as a circle with a cross. And this is a small section of this toroid. Anyway, in this case also, that is, when a core is introduced into the toroid, and then the magnetization of the core takes place, and because of magnetization, magnetic dipoles will be induced in it, and these magnetic dipoles, it can be represented as a current loop, and this current loop can be represented by small circles. That is, in the interior of the core, these small circles, when we are considering the small circles, the current loop, adjacent current loops, if we consider the adjacent current loops, then the current in the adjacent current loop will be in the opposite direction. So it will cancel each other. And only at the periphery, that is the outermost of the outer region, only we can see the circular current loops. And even on all the current loops inside the a core, it gets cancelled because of the opposite directions of the current in each adjacent loop, and hence there is no net current inside the core, but the current in the outermost of the outer region of the loop, it remains uncancelled, and the current which is circulating around the outermost of the outer region of the ring, it is called the Amperian surface current, and it is represented as IS. And this Amperian surface current IS and the magnetic vector M can be related by a simple relation. And for that we are considering the cross-sectional area of the ring as capital A, and L the circumferential length of the ring. Therefore, the volume of the ring is L into A. And the ring behaves as a large magnetic dipole of moment M. And the magnetic dipole moment can be represented as the product of the current and the area. That is, the magnetic dipole moment small m is equal to Is into A, because here we are considering the Amperian surface current. Therefore, the magnetization M vector can be represented as the magnetic dipole moment induced per unit volume. That is, the magnetic dipole moment M divided by volume, and this M magnetic dipole moment can be represented as Is into A, where divided by the volume is the area into the circumferential length, and is equal to the I divided by L. Here the I is the Amperian surface current. Hence, the magnetization can be represented as the surface current per unit length. That is, the magnetization M is equal to Is divided by L, where Is is the surface current, Amperian surface current. And this current is called the magnetizing current because it magnetizes the core. Then we can consider the magnetic induction vector B. That is, the magnetic induction vector B within the material of the ring arises due to the free current I in the windings as well as due to the magnetization of the ring itself. So the B can be represented as B is equal to mu 0 into the current which is produced, which flows into the circular loop, that is the free current, that is Ni divided by L plus the surface current, Amperian surface current Is by L is equal to mu 0 into Ni by L plus the Amperian surface current per unit length can be represented as the magnetization M. That is where Ni by L is the free current per unit length. Here Ni by L is the free current per unit length, and Is by L is the Amperian surface current per unit length. But we know that the Ni by L, we have already studied the magnetic field intensity vector H. Then capital N by L. N is the total number of windings divided by L is the circumferential length. This capital N by L, it is equal to small n, that is number of turns per unit length. That is N into I, where number of turns per unit length is capital N by circumferential length L. Therefore, H is equal to Ni. Then B will be becomes B is equal to mu 0 into H plus M. And this is the relation connecting the three magnetic field vectors B, H and M. And when there is no magnetic material present in the core of the Rowland ring, then the magnetization, there will not be any magnetization, and the M will be 0. Then the equation becomes B is equal to mu 0 H. And next is the magnetic susceptibility. It is represented by the symbol chi M. And the susceptibility is a property which determines how easily a specimen can be magnetized. So it can be represented as the ratio between the magnetization vector M and the magnetizing field vector H. That is, magnetic susceptibility chi M is equal to the magnetization vector m divided by the magnetizing field h, m by h, and it's a dimensionless number, it has no unit. And the magnetic permeability next is the mu, it is represented by mu. And the magnetic permeability means it's the ability of a material or a medium to permit the passage of magnetic lines of force through it. That is, the magnetic permeability means it's the ability of a material or medium to permit the passage of magnetic lines of force through it. And this magnetic permeability of a medium can be represented as the ratio of the magnetic induction vector B to the magnetic field intensity vector H. That is, mu can be represented as mu is equal to B divided by H. Next is relative permeability, and it is represented by mu R. And the relative permeability can be represented as the ratio of the magnetic permeability of a material to the permeability of free space. And the permeability of a material can be represented as mu, and the permeability of free space can be represented as mu 0. Therefore, the relative permeability mu R is equal to mu by mu 0. Then the relation between mu R and chi m, that is the relation between the relative permeability mu R and magnetic susceptibility chi m. Consider the relation connecting the three magnetic vectors B, H and M. Here, the magnetic susceptibility can be represented as chi m is equal to M by H, or the magnetization vector M can be represented as magnetic field intensity vector into the magnetic susceptibility. That is, M is equal to H chi m. Therefore, B is equal to mu 0 into H plus H chi m instead of M H chi m is equal to H can be taken outside, that is mu 0 into 1 plus chi m into H. But we have already studied in the magnetic field intensity B is equal to mu H, where is mu is the magnetic permeability of the material or a medium. That is, mu is equal to, therefore, we are substituting the value of B in the left hand side of the above equation, and in the right hand side we are considering the equation. Then we get B is equal to mu H, and B is equal to mu 0 into 1 plus chi m into H. That is, H and H will cancel, and finally we get mu is equal to mu 0 into 1 plus chi m. And in vacuum, the mu is equal to mu 0. Therefore, and chi m is equal to, that is magnetic susceptibility means in vacuum there is no material, so there is no magnetization takes place. Hence, the magnetizing vector m is equal to 0. Therefore, chi m is equal to 0, and hence the magnetic induction in vacuum is B0 is equal to mu 0 H. And also the ratio B by B0 is called mu by mu 0, and it is called the relative permeability. Therefore, the B by B0 or mu by mu 0 is called mu R. Therefore, mu R is equal to 1 plus chi m. The unit of permeability is Weber per ampere meter.